How long it was there? For how much was it there?
Didn't notice. Just saw it now.
Okay, it's fine. They can catch up. You know, they sharp. They can do it. Sama, you can do it. There. Bending moment at E. Bending moment at E. How many forces are to the left of E? 4. What 4 are they? 1 up, 3 down. Right? 27. Oh yeah, all this will be equal to 0, right? I understand it's all equal to 0 because the system is in equilibrium. Okay, so far we're all good. Now we got everything we need to draw our diagrams. So let's draw our diagrams. Right? So three, 2, 20, 10, 30, 27. Right, now let's draw our shearing force diagram. You will start off by drawing a horizontal directly below your loading diagram. Okay, this is like your 0 line. You start with your first point. First point here is A. Upwards forces would be a positive, downwards force would be a negative. So this moved up positively until 27 kilonewtons. Stayed like that for 2 meters until it had a force coming down or concentration load of 20, which would bring this to 7 kilonewtons. Right? Stayed like that for 3 meters until another concentrated load of 10 got added. So that will take you to minus 3. You understand why, right? Because 27 minus 20 is 7. 7 minus 10 is minus 3. Okay? That stayed like that for another 3 meters until 30 kilonewtons were added onto the beam. So it will be minus 3 minus 30, which is
minus 33.
that continued for about 2 meters until you have your support of 33 kilonewtons, which brings everything back into equilibrium. So all this here is your shearing force diagram. Is everybody okay with that? Not bad? Good. Right, let's do your bending moments. So your bending moments.
So the horizontal line is 10 meters, or it doesn't matter. But it must be
Yeah, from here to here is 10 meters. Okay, and it helps to draw it in scale because say when you come to your bending moments and stuff, everything if it's nicely below each other, you find, right? So this is your 0 line for your bending moments. That's 0. So let's start there. Your bending moment at A is what? That's 0. Okay. Bending moment at B, yes.
54 k's.
Say 54 is somewhere there. Bending moment at C.
75.
And then your bending moment at D is
66.
66. And then it goes back to. So because this is a concentrated loads only, each line that you draw would just be straight sloping lines. Okay, so you'll just join the dots. And see why they tell you to draw it to scale as well is because the shape of how your bending moment comes. If this was 3 meters but you drew it like all close together, your diagram could look something like this. Something, like off, it won't look right. Okay, so all this here is your bending moment. What should be the maximum bending moment here?
75.
Okay? Cool?
So all these points are where the beam shear. All those points, A, B, C, and D.
Yeah.
It's all points at shear.
That it?
Taking
The beam sheared.
Shear. Oh yeah, no, well, all this here is points where force acts on it, acts onto the beam.
But where is the point where it's going to be the most?
The
Will be
height.
75.
And so anything past this point here would obviously break.
Oh, okay.
So this is before it broke,
Oh, okay.
right? So even like how Chemba said, when we put in the stuff, how would the beam eventually look after time? This is how it will look. It will start to bend.
Depending on the probability with that 75. That's
If you keep on adding more weight, yeah, it's gonna crack.
Okay.
Right?
It'll break there first before the 54.
Before, because here it's obviously lower. It's not the bending is not as
So
bad.
the weakest point is the 75.
That's it.
Okay.
Okay. So you have any shells? Shouldn't have issues now.
I can't stay up.
Also, you knew this before you did
Yeah.
So now in the exams and stuff, what exactly a similar question like this?
Yeah.
No.
No, I'm joking. No, I'm joking. You get something like this, but obviously they'll add uniformly distributed loads. And uniformly distributed loads, you'll see the way your diagram would obviously be different. How much time?
It's 2 o'clock.
It's 2 o'clock. Jesus Christ.
I need to have this hand, it's fine.
Yeah.
I think we should.
I have to ask.
Huh?
It's 2 o'clock. I have to ask.
I think we're ahead with the getting up.
I want to eat. I'm hungry.
Huh?
I want to eat.
What do you eat? Not eat.
No, let me finish. I want to do this one so I can give you all one homework question, which is a buster to our own lad. And then tomorrow you're going to come playing on me.
There has to be a catch.
Always. Is it ever that easy in science? But so far it's okay, right? You see, the only difficult thing that comes is, you know when you're doing your bending moments, and when you have a uniformly distributed load, you have to take into account that portion of it when you're working at certain points. You're going to see what I'm talking about, right?
I think this is better than first.
No, but you see, why it's a bit easier is because they give you the points where you must work out your bending moments at. When they give you a story and you have to draw your loading diagram first, then decide now, hey, I need to work on bending moments at here. That's when it becomes difficult. Right? So, I'm looking at example 4.6. Example 4.6 is where I'm going to stop with this part of the section of bending moments and diagrams. Example 4.7, you can attempt. It's going to be similar to how we did 4.6. And example 4.8 is on how a cantilever would be drawn.
So once we do this exam, we're done with the section.
We're done with forces, shearing forces, and bending moments. Then tomorrow, after I mark that activity question with you, we're going to move on to some tricks. Okay? Where am I?
These are very quick here, right?
Yeah, see, 4.6 is more like how they will ask you now, right? This is like how they will ask you to exam. You have time to?
No.
Oh.
Yeah, the coordinates of that is.
Okay, so let me just draw. Okay, so they tell you a simple beam is 6 meters long. Beam is 6 meters long. A uniformly distributed load of 2 kilonewtons per meter extends over a length of 2 meters from the right hand. From the right hand direction. Okay, so this says 2 meters. And it has a magnitude value of 2 kilonewtons per meter. The beam also carries a concentrated load of 3 kilonewtons located 2 meters from the left end. It is supported at its ends. That's information you give, right? So, what would we do here?
Calculate.
Calculate the
you convert into a concentrated load. The concentrated load would act at the middle. This would be 2 times 2, which is 4 kilonewtons. Distance here would be 1 meter. Distance here would be 1 meter. What's this distance in between? 2. See, you're getting it now? You're looking angry, but you're getting it. You have a call. Right. Okay, all the information given to us. First question. Calculate the reaction force A and B. Oh, I never read how they call. Okay, so they call this point A, they call this small a, small b, big B. Right? So A is there. Right? Calculate the reaction forces RA and RB. How would you do that?
Check moments about A. Moments about A.
Sorry, repeat what?
Okay.
The diagram is different.
Sorry, they call it B and C.
What's the X? The 2.5 meters.
No, wait, that will come later.
Shearing force.
That will come later.
The shear.
That will come at question E. That's why I never draw it down. I don't know if you right? Check the moments about A. Clockwise moments is equal to anti-clockwise moments. So, what do we do?
Or if we get the first point.
Say it like how I would say it here.
When you're looking at A, first they're acting clockwise.
That will make them tendency to move to
All your downward
on B.
forces.
So, if we're looking at A, what would cause the other end to move in a clockwise direction? What would cause it? Downwards force, right? So your first downwards force is 3 kilonewtons. How far away is that from A? 2 meters. Plus your concentrated load, which is 4 kilonewtons. And how far away is that from A?
5.
5, right? 2 plus 2 plus 1, right? So if, just see,
Yeah.
So it's
the
2
full length of the beam is how?
6
6 meters. Okay, and then that's 2 meters.
So this beam, this uniformly distributed was 2.
Just minus
It lacked at the middle, so it would be 1 and I did.
Just minus
Okay.
the minus.
Right?
Okay.
So if downwards forces caused a clockwise motion, upwards force will cause a anti-clockwise motion. So because we're looking at A and RA acts at the end, you know it's going to be 0. So we say RB is how far? So you see, I don't take it, I'll pay attention, I'll give you a time after that.
6 meters.
6 meters. Okay. So 3 times 2 is 6, 4 and 5 is 20. So this will be 26 is equal to 6 RB. So 26 over 6 is
4.3 recurring.
Yeah, 2 meters. Oh, 2.
kilonewtons, right? Is equal to reaction force B. Then you say take the moments about B. Then you say,
Should I put the thing on the right so you can help me on the
Yes, and then
no, I'm going to leave that board for diagrams.
Okay.
Clockwise moments is equal to anti-clockwise moments.
Yeah, upward force.
Now, in this instance here, how would I say it?
From point
What would I say after this?
the moments from B will cause A
What will
to
cause A to move on the
clockwise.
clockwise direction?
A
Say what you said again?
A to move.
No, you say what you said again?
When you have B,
Yeah.
one will make it to the other end to move.
That's not what you said. That's not what he said. That's not what you said. Right? That's not what you said. Right. But if we're looking at B, what would cause the other end to move in a clockwise direction? So your upwards forces would cause you to move in a clockwise direction. So RA is how far away from B?
6 meters.
And because RB acts at point B, its distance is 0, so that term will cancel off, right? Now if up caused a clockwise motion, down would cause a anti-clockwise motion. So your first force, which is your 3 kilonewtons, is how far away from B?
4.
Yeah.
I don't know, I'm asking you else, Himanshu. Right. Your uniformly distributed load, that force of 4 kilonewtons is how far away?
1.
Is it here? 1 meter, right? 4 and 1. So this is 6 RA is equal to 16.
Yeah.
And then RA is equal to 2 point some change. 2.7.
Divided by
16 divided by 6.
6.
So this is 2.666 kilonewtons. Yeah, right? And you have to do the test, okay? Upwards forces must equal to downwards forces. Your two upwards forces, 4.33333 plus 2.66666 is 6.99999, which if you round it off will become 7. 3 plus 4 is 7. So your upwards forces is equal to your downwards forces. Your reaction forces is now equal. I mean, your reaction forces are placed, right? This should help you when you're going through the video, right? Because you'll get used to it, right? Then they tell you, calculate the bending moments at A, B, C, well, small b and then big B, right? So, for B, when we say bending, I'm just doing this for the first few times, you do it after this, you must remember it, right? So when we're saying bending moments, we'll say to the left of a point. Clockwise moments will be a positive value, which will instantly make your upwards values positive, and anti-clockwise moments will be equal to a negative value, which will make your downwards values negative. Right, so let's start. Bending moments at capital letter A will be equal to what? Everything to the left of A, which is 0 kilonewton per meter. Bending moments at small letter B, right, is everything to the left of small letter B, which is what? RA. So it's a positive value of 2.666, and how far away is that from B? 2 meters, which would make it 5.22222. Right? Then you look at your bending moment at small letter C, which would be equal to what?
C is 4 pi.
So it will be, you start
No, it's
from
not.
B,
It's
B.
B.
I drew C at the wrong place.
RA.
Sorry, C they got it at here. Okay? So where C is?
C is 4 meters from A.
4 meters from A. What A?
What's A?
Okay, you got to figure out for each other.
Confusing us.
You confused me. When I start asking you about this, how do I say it? Bending moment at C.
Yeah.
You look at everything to the left of C. You're telling me 4 meters from A. What A?
What if you work on B and then work on C?
It's RA times.
C, right?
2
Bending moment at C. You look at all your forces to the left of C. How many forces do we have? What is each force called? Your RA and the 3 kilonewton. Right?
Yeah.
So your RA is obviously moving up. It is a positive value. So this here is 2.666 times 4. Because it's RA is 4 meters away from point C. 2 meters plus 2 meters. Right? The other force you have is the downwards force of 3 kilonewtons, which would be negative 3. And how far away is that from C? 2 meters, which is equal to
4.664.
Last point they asked you for, because see they asked you for A, B, C and then capital letter B again, right? Capital letter B is on the end. How many forces act to the left of it?
Three.
3 forces, right? So, how would you do this? You would say positive 2.666
times 6.
times 6 plus negative 3 because it's a downwards force. And how far away is that from B? 4 meters plus what?
That 4.
4 carry.
Negative 4
Times 1.
times 1. Right? What's
0.
0? Don't you think it would have been nice if you just wrote 0 at the start? Okay.
Sorry man, I just wanted to check up something. You changed something there, right? So you said there's a force on C. No, on the drawing there. You moved the C from the middle
Yeah,
to the
because
left
that's where they asked you to
work out.
calculate it at.
Okay.
Right? If you wanted
But
to,
it's not a force,
you
it's just,
could
they
have,
just want
yeah,
to
it's
work
a
out
point
points.
on the
Okay.
beam, right?
Okay.
If you wanted to, you could have also worked out something called point D there. And I'm going to tell you after this how you will do that. Okay?
Yeah,
Because I don't want to change how you would calculate the bending moment, because say if I call this point D, right? And I asked you guys to work out the bending moment for me at point D.
Yeah.
Okay? We'll say it as normal. Bending moment at point D.
Yeah, to the left.
D.
Minus 4.
How many forces act to the left of it?
2.
2 forces.
Yeah.
These are 2 forces.
Yeah, it's two forces.
C is not a
Sure.
force.
Are you sure it's only 2 forces? Right?
What about the, you know,
C. Not I'm saying C, I'm saying look, right? Where D is.
Yeah.
Okay? You have 1, you have 2. See the small portion of your uniform beam? Isn't that still acting on it? It's still acting on the left of it, right? But you can't take this value of 4 because that 4 is the average of the entire beam. So how would you do something like that? You would have to say, we know that this part here is 1 meter, right? 1 meter times this. So you're basically you're converting the small portion into a concentrated load.
Well, you're basically cancelling out the meter section of the 2 kilonewton meters, right?
See, the kilonewton per meter they give you is like a magnitude value, right?
Yeah.
Depending on the size of the load,
Yeah.
we multiply, the distance of the load, we multiply by the distance to get an average of that entire thing, right?
Yeah.
Which we use for calculation purposes,
Yeah.
right? Now, imagine if this whole part wasn't there, this whole right hand side of D wasn't there or didn't exist, it's gone, right?
Yeah.
And this was your uniformly distributed load. How would you work out that force?
That's what I'm saying. 2 kilonewton meters, right? By saying multiply it by whatever the length is, 2 kilonewton per meter.
Yeah,
So that meter section
take it out.
between B and C would actually be equal to 2 kilonewtons. Am I right?
Because you multiply by 1, but I'm saying for any, in a general
Even
circumstance,
if it was a
you
good
just take the
meter.
distance of it
Yeah.
and multiply, but that doesn't give you the force.
Yeah.
And your force will act where?
In the center.
On the left hand side.
The center.
And then what?
No, not the center.
It's right, on the center.
center of the
On the center of the, guys, it's a uniformly distributed load, right?
Yeah.
When you convert it to a concentrated load, where does your force act?
On the center.
On the center, right? So that 2 kilonewtons you worked out
Yeah.
will act on the center here and be 0.5 meters away from D. Do you understand what I'm saying?
Yeah.
Right. So when you are working this out, you would have said 2.666 multiplied by what's the distance of RA to D? 5. Right? You're understanding what I'm saying?
Yeah.
Everybody understands it, right? Plus, this is not related to this calculation. I'm saying, but if you got this, how you do it. Minus 3 multiplied by the distance of that to D, 3. Plus the third force of the 2 kilonewtons, right? It will be minus 2 multiplied by the distance of it from D, which would be 0.5. Okay, if you are to draw it on the diagram, this is your beam, right? And this is your uniform, the original one given to you, right? And I said that I'm calling this point D. Okay, this portion here, remember this was 4 kilonewtons and it was 2 meters, 1 meter. It was 1 meter. And I want to know what this portion is. I would have taken, and remember this beam, we said it has a magnitude of 2 kilonewtons per meter. I will make this now, this portion here, into from a uniformly distributed load into a concentrated load. So to work out the force that would act in the center of this, I would have said 1 meter multiplied by 2, which will make it 2 kilonewtons. And the distance away from D would become now 0.5 meters. Do you understand what I'm saying? Right? And you're going to see in the activity question that you're going to do for me, you're going to have to use that when you're working it out. Okay?
So these tricks involved in this also.
Yeah. But just work this out for me and tell me what you get. That value has to lie between this and this.
We're like about 2 point something.
3.33.
Which lies between this. Because remember, the curve when you're drawing it, it will, once you hit that uniform or the uniform distribution load, it's gonna come something like that back to 0. Okay, so obviously a value has to lie between. Okay, that's just a side thing. Okay, back to where we were. But obviously remember that for your calculation. Okay, then they ask you to draw the shearing force and bending moment diagram. So this is our loading diagram, and this is RA, which is equal to 2.666 kilonewtons, and this here is RB, which is equal to 4.333 kilonewtons. We have a force here of 2 meters, which is 3 kilonewtons. You have this uniformly distributed load with a force of 4 kilonewtons. This is 1 meter, this is 1 meter, and it's pinging. This is 2 meters, and A, and B, this is B, C. Right, and let's draw our shearing force diagram. So, 0, 0, your horizontal line first. Right? Let's start from the left end, you move towards your right. Upwards values we add, downwards values we subtract. So this moves up for 2.666 kilonewtons. Stays like that for about 2 meters until it's subtracted by 3. So it will move to
0.334.
continues like that for another 3 meters until
-4.
the concentration load, right? It's because obviously now that magnitude we know is at the center. So this will continue until here. Here. Right? And you subtract 4, which will take it to minus 4.334 kilonewtons. That will continue for another meter until your upwards force, where you'll add 4.333, which brings it to 0. Okay? This here is your shearing force diagram.
Okay.
Are we drawing it to C or to the center of
The D. It's really
Yeah, I'm supposed to do it.
I'm sorry.
to see.
Good work. What else is wrong with the diagram?
Untidy.
It's really
Now you laugh, because of that I want you to tell me what's wrong with this diagram?
What's
We're
wrong?
supposed
Yeah.
to move.
Because I want to see how long we carry on and be happy about it. Now you feel like you must tell me now what's wrong.
Give me some time.
Yeah. What's wrong with how we drew the diagram?
It's not to scale.
No.
No,
Something
it's,
about the.
I know it's not to scale. I don't have a ruler.
Yeah, your 2 meters is small there, your 2 meters is
Yeah,
big.
exactly.
Yeah,
That's
yeah.
fine.
That's not the scale, sorry.
Remember, we said for a concentrated load.
Yeah.
When you're drawing it on a shearing force, it's a vertical line.
Yeah.
When it's a uniformly distributed load, when you're drawing it on your shearing force diagram, it's a sloping straight line. So when you came to this point C, right? So this here would have been straight.
Yeah.
The moment you introduce your uniformly distributed slope or line, whatever, right? That would go
Oh, slow.
slope
Okay.
until negative 4.334, and then you'll add obviously straight up. So all of this is
So that
your.
would be a-
So if
The slope for the shearing.
But it's.
So that's how at point D, if you took it down, you would end up with that value then you'll be.
yeah, because now this is shearing force, not bending moment.
No, but what I'm saying is if we did take it down, we should have the same thing.
Yeah,
We would have ended up with the same thing.
yeah. So you're talking about that if you come from here and you come.
Yeah, point D.
Yeah.
If you took it down, it should come up on the same slope.
It should cut here,
It should come
and
up-
then it will go down to your bending moment at that specific point.
Okay.
Okay, cool with this. See now how we're introducing how the differences in how this diagram should look. A concentrated load on a shearing force diagram comes vertically down. A uniformly distributed load on a shearing force diagram comes at a slope. Whether it's an upward slope or a downward slope, most of the time it will be a downward slope, right? Because you'll have the weight acting downwards, but you'll draw it at a slope. Okay, understand?
Yeah.
Okay, now let's see your bending moment diagram. Okay, so you start at your ends. When you're redoing this example, try to draw it as accurately as possible, directly one below the other, right? First bending moment at A is what? 0. Your bending moment at B is, at small letter B is?
5.3.
So let's say 5.3 is here. Right? Kilonewtons per meter, right? Right. Your bending moment at C,
4.66.
4.662.
and then it goes down at D to, not D at big capital letter B, to 0. Right? Now remember, with a concentrated load on a bending moment diagram, you'll draw the line as a sloping line. Okay? Don't confuse what I'm saying with shearing force and what I'm saying here. For a shearing force diagram, a concentrated load is a vertical line. Vertical line. Concentrated load, a point load. Right? On a bending moment diagram, a concentrated load will be shown as a sloping line. For a uniformly distributed load,
It's a curve.
not curve, man. Why you getting
The
curve from?
bottom one now.
No, it must be
It's not a curve, it's a straight. It's the word is straight. How can it be curved?
No, I'm saying. for
Okay,
the-
listen to what he's saying, then you're going to get
Listen to that.
the next part.
For, I'm sorry again, for a concentrated load, a point load, on a shearing force diagram, when you are drawing it, it will be a vertical line.
Yeah, okay.
And on your bending moment diagram, it will be a slope, a straight slope
Yeah, okay.
line. Okay. And then obviously from here, it will move to there.
Right.
For a uniformly distributed load, on a shearing force diagram, it would be a straight slope. But on your bending moment diagram, it will become a parabolic curve. So from here, and when you're drawing it down, you draw it like something like that. Right? The curve. Okay?
Oh yeah.
Because remember, it's bending, but throughout. But as it moves closer to the support, obviously it will bend less. So which is why you'll have a higher bending force towards the end that's away from the support. Because as it moves closer towards it, it's gonna obviously it's gonna bend less. Right? But remember there's still 4 kilonewtons acting at each point. Right? So this here is your bending moment diagram. do you all understand what I did? Okay. Oh,
So let's attempt it, then we'll tell you.
right. Try to do it as slowly as I could, and try to get your.
Yeah, but I think all these examples get viewed again. This
Yeah.
Obvious, yeah. Because I think when you're doing it,
Yeah, because I'm telling you, when you're getting stuck, you all need to obviously.
Bending moment, shearing.
Oh, we're not done. We're not done. I'm actually done. So they wanted that. Now they asked you to calculate the maximum bending moment. Okay? Your maximum bending moment, you can do one of two things. This is D. This is C. Okay? You can do one of two things. You can either read it off the graph, or you see in the instance of when you have uniformly distributed loads, right? When you join it, too many parabolic curves, you're working it at different points. There could be a point where when you worked it out here, your parabolic curve does that. Right? So now your maximum is not here, it's actually there. Okay? But remember I told you that, and this is what you need to remember, is that your maximum bending moment is when your shearing diagram cuts,
could be a P.
or where the shearing, what is next word? Maximum bending moment can be obtained when shear force diagram cuts the baseline, which is your X line, right? Which is that zero line. Okay, that's when you would obtain, because look at it, where it cuts it here, if you keep on going down, you got what? Your maximum bending moment, right? So you can either read it off the graph, or where it cuts it here, right? Remember there's a certain distance up there. You could just say 2 meters multiplied by whichever form, you can work out the moment of it. So you could say, if it cuts it basically at this point here, you work out the moments, everything to the left of it, right? Everything to the left of it is just RA. And RA acts how many meters from that point? 2. So the value would be 5.33.
How come we just write the answer because it's already there?
You can, but I'm saying in an instance where you have see like how you had that one when I showed you the example of that bits of uniformly distributed load, right? And that will be the point where the maximum is happening, but you need to work out the length of it, that smallness, okay? So, but anyway, this here will be equal to,
Basically, the read to that point B basically.
yeah, like how they did over here. See, they say take X from A, maximum bending point is equal to 2.667 times 2, which is equal to 5.333.
The method is right there. We couldn't get point B.
Yeah, but you just write the same thing again.
And if we had like that other example, we would have had BMD, and we would have had the answer there anyway. We still have to work it out.
Because sometimes they ask you for that length. Because see, remember what I said, right? When it's coming up to this point here, right? When you come at a certain point, well, if you're coming from the left hand side, and if your curve starts, right? The point you know could be here, but your maximum is here. You get what I'm saying?
What do you mean? Don't we always start our curve from the point anyway?
Okay, say for example you never worked out C
Okay,
and you worked out D,
alright.
right? Your points that you worked out, you're showing the value only from here. You get what I'm saying?
Okay.
You're not showing it from C where it actually started here. Remember D will be here.
But won't these points also start the same with the curve?
Yeah, but you only start your curve from here because that's where you worked out your first. But it's supposed to be curving earlier. But I'm just saying, ignore if all of this wasn't there, right? And if it was just this point here will only start here.
Yes.
But in actual fact, all of this here is still higher than it. You get what I'm saying? So you need to work that out.
So I might just
So that's when you say now. all
You know where
points
you're gonna
will
see it.
get
You're gonna see it in your activity.
Oh,
Well, they might just pick a point and say,
Calculate
calculate
it.
what.
You will have to work out the distance. Because if they give you a diagram, or what happens in the instance if they gave you the diagram? Right? They put the bending moment, they gave you a bending moment diagram, they gave you certain points. Right? And they tell you calculate the maximum. Or the distance of the maximum. You only know the final values. Right? You will need to work backwards and obviously get it. Okay? Next one they ask you, calculate the shearing force QS and the bending moment MS at a distance of 2.5 meters from the left direction. So,
Oh, it's not saying.
they're basically telling you that at this point here, now is where you had your bending or your breakage. Now remember that there when we did it earlier, when we started the section, how you would work it out, right? So this here is 2.5 meters. So QS would be your shearing force. Now remember from our sign conventions earlier, what I said, for everything to the left, upwards would be positive, downwards forces would be negative, which is how we even got how we do our bending moments here. It's based on the same principle. Okay? So, in this instance here, if this is where the line is, how many forces are to your left? 2, right? Your upwards force and your downwards force. So, in this instance for forces, you just add and subtract your forces, right? So this would be 2.666 minus 3, which is equal to 0.334 kilonewtons. Fine? Fine?
Yeah.
Good. Right? Bending moment. Bending moment would be just that forces multiplied by its distance. Okay? So 2.666, how far away is it from the X line?
2.5.
2.5 minus 3. How far away is the 3 kilonewtons from the X line?
0.5.
0.5. Everybody understands why. Okay? So this here is 0.5, which is equal to
5.165.
and that, guys, is bending moments, shearing force. Who's completely lost?
Yeah. How many marks is it? 25 marks?
No, like I'm joking. Everyone, try. This could be, like in the syllabus breakdown when I was telling you at the start the weighting levels of it. What was the weighting level?
You had the stats was 15%.
So this could be like a 15-mark question.
15 mark.
But see
And
like
you still
how,
got 10 choice to go as part of stats.
oh shit, this could be a 10-mark question.
Yeah.
Aye,
Right.
so long.
See like how A, B, C, D, E, you will have part marks for each thing. No, say
So
maybe
centroids
12. Say maybe 12 marks. Centroids, when you're doing your answer for centroids, right? See like how it is on page.
Yeah. I think it's another for 12 marks.
See page 96.
Yeah.
At the top of page 96, how they do the table there.
Yeah.
That's how you draw your answer.
That's a lot of writing.
For what? Centroids.
Yeah, that's how you do your answer. It's a very short answer. Oh my god.
Get the slides.
Hey, see, he wants the same accident that the TV accident again.
Yeah, now all the files almost fell on me.
Yeah, we will blame this time.
You. The class wasn't paying attention.
See what calculation wrong.
Then guess so you're okay with that?
Yeah.
Yeah.
Yeah, will be okay with it. Your activity or your homework is activity 4.2 question 1. It's not an easy one. It's a thinker. The solution is not in the back. I don't ask me why. But you all get it.
4.2.
Activity 4.2 question 1. That's your conversation.
check it out. Check this one. You know, whenever you give us those difficult sums, it gets very clear.
Answer activity 4.2, question 1.
Sure.